San. Welcome to your deep dive. Today we're tackling a topic that's, well, invisible but all around us. Radioactivity.
Yeah, and we're using a really interesting source of technical text from back in '94, but the core science, still absolutely solid.
Right, so our mission is to kind of pull out the key stuff, the physics, how it's measured, the biological side, and maybe surprisingly where most of our own exposure comes from.
And to even start talking about doses and effects, scientists needed a reference point.
Ah, the standard man. Sounds a bit clinical.
It is, really. It's a theoretical baseline for all the calculations.
Yeah.
Defined as 20 to 30 years old, 170 centimeters tall, 70 kilos.
Okay, so specific average.
Very specific. They even break down the chemical composition. This 70-kilogram standard person
Yeah.
is 65% oxygen, 18% carbon, 10% hydrogen by weight.
Oxygen, carbon, hydrogen.
Got it. And that's important because that's what radiation interacts with, right?
Precisely. But before we get to the damage, we really need to understand the scale we're talking about. It's mind-bending.
Okay, so atoms, the basics. Right. You've got the nucleus, protons, neutrons, held together by that strong force and electrons orbiting around it. But the key thing is the emptiness.
How empty.
The source uses a great comparison. The nucleus is nearly 100,000 times smaller than the whole atom's electron shell.
Wow. Yeah, think of it like this. If the atom was as big as a giant TV tower.
Okay, the nucleus would be like a match head sitting at the bottom.
So it's mostly just space, but incredibly dense at the same time.
Staggeringly dense. Take just 1 gram of iron, 1 single gram. That contains roughly 10 to the power of 22 atoms. 10 number.
That number. It's just impossible to really picture. It
Yeah.
is. And the source has this thought experiment. Imagine spreading that 1 gram of iron evenly over a whole city, say, Hamburg. Okay, spreading it super thin over a huge area.
Even then, you'd still have 1.3 times 10 to the power of 13 iron atoms on every single square meter.
13 trillion atoms per square meter from 1 gram.
It just shows you how incredibly packed matter is at that level.
So these tiny, dense things, atoms, but
Yeah.
sometimes they're not stable.
Exactly. That brings us to nuclides and isotopes. A nuclide is just any specific type of atomic nucleus, defined by its proton and neutron count.
And isotopes.
Isotopes are atoms of the same element, so they have the same number of protons but a different number of neutrons. Different mass.
Like hydrogen, right, there are different kinds.
Perfect example. Normal hydrogen, H1, is just a proton, but add a neutron, you get H2 deuterium.
Right?
Add 2 neutrons, you get H3 tritium, and that extra neutron, or an imbalance, can make the nucleus unstable, a radionuclide.
And that's where radioactivity comes from, an unstable nucleus trying to fix itself.
Yes, it spontaneously transforms, spits out particles or energy waves radiation to reach a more stable state.
Okay, let's get into those main types of radiation, the source details. Alpha, beta, gamma, they sound quite different.
They are very different in nature and behavior.
Start with alpha. What exactly is it? You called it the heavy hitter before.
An alpha particle, alpha is basically a helium nucleus. 2 protons, 2 neutrons, bundled together and ejected.
So it's relatively big and heavy for a particle.
Yeah, which means it's comparatively slow, moves around 15,000 kilometers per second, and it's densely ionizing. It does a lot of damage in a short path.
But it doesn't travel far?
No, not at all. Because it's bulky and charged, it gets stopped easily, only about, say, 4 to 7 centimeters in air. A piece of paper stops it completely.
Okay, hits hard, poor penetration. What about beta radiation?
Beta is different. It's actually a fast electron, or sometimes it's opposite, a positron that gets shot out. This often happens when a neutron turns into a proton inside the nucleus or vice versa.
And it's faster.
Much faster. Its speed can be up near the speed of light, and compared to alpha, it's loosely ionizing. It spreads its energy out more.
And range. How far does beta travel in simple terms?
Significantly further than alpha. It can go several meters in air. But in your body, in soft tissue, maybe only a centimeter or 2 deep, it takes a thin sheet of metal or plastic to stop it.
Right, then there's gamma. That's not even a particle, is it?
Correct. Gamma radiation is pure energy. High-energy electromagnetic waves, photons.
Like light, but much more energetic.
Exactly. Travels at the speed of light, about 300,000 kilometers per second. It often comes after an alpha or beta decay, like the nucleus settling down and releasing extra energy.
And the source mentioned it's basically the same as X-rays. Physically, yes, high-energy photons. The only real difference is the origin. Gamma rays come from the nucleus. X-rays come from rearrangements in the electron shells outside the nucleus.
Okay, so we have these different types, alpha, beta, gamma. Now, measuring them seems complicated. Why all the different units? Becquerel, Gray, Sievert. Why not just measure the energy?
Well, because the amount of radiation, the energy deposited, and the biological damage caused are all different things. We need units for each step.
Right. So let's start simple.
Yeah.
Activity, Becquerel, BQ.
Activity is just the rate of decay. How many unstable nuclei are transforming or decaying per second? So 1 becquerel, 1 BQ is simply 1 decay per second.
It measures the source's hotness, so to speak? Kind of, yeah, how frequently it's emitting something. You might also hear the old unit, the Curie, which is huge, 37 billion becquerels.
Okay. Then the next step is the energy actually absorbed by something, like tissue. That's the gray. Gay?
Yes, the Gray measures the absorbed energy dose. 1 Gray is 1 joule of energy absorbed per kilogram of material. It's purely physical energy in per mass.
But you said that's not enough for biology.
It isn't, because 1 Gray of absorbed energy from alpha particles does vastly more biological damage than 1 Gray from gamma rays.
Ah, okay. This is where the Sievert SV comes in, the equivalent dose. How does it account for that difference?
The Sievert is the key for biological risk. It takes the absorbed dose in Grays, D, and multiplies it by a weighting factor called the quality factor, Q. So the equivalent dose, H, equals D times Q.
The quality factor, Q. What does that actually represent?
It represents how effective each type of radiation is at causing biological damage based on how densely it deposits its energy.
So what are the Q values for the main types?
This is the crucial part. For beta and gamma radiation, Q is 1. Their damage is sort of the baseline.
Yeah.
But for alpha radiation, remember, densely ionizing heavy hitter, the quality factor, Q, is 20.
20. So for the same amount of energy deposited, alpha does 20 times the biological damage.
Roughly, yes. That's why you absolutely must use Sieverts when assessing biological harm, especially if radioactive material gets inside the body, where alpha can do direct damage to cells.
That really clarifies why the units matter so much. Okay, so let's trace that damage. How does radiation actually mess with our cells, that 65% oxygen, 18% carbon structure?
It happens incredibly fast, in stages. First is the physical phase, instantaneous. The radiation zips through, knocking electrons off atoms, ionizing them, or just exciting them. Chemical bonds get broken right away.
Okay, physical disruption.
Then the chemical phase kicks in, still very fast. Because cells are mostly water, oxygen, and hydrogen, remember? The radiation breaks apart water molecules. This creates nasty things called free radicals, highly reactive chemicals like hydrogen peroxide, which is basically bleach. These chemicals then attack other molecules nearby.
Including our DNA, which is carbon-based.
Absolutely. DNA is a prime target, and if the cell can't repair that chemical damage properly,
We get the biological phase.
exactly, cell malfunction, cell death, or critically, mutations if the DNA damage isn't fixed correctly.
Mutations, like errors in the genetic code.
Precisely. Could be small changes, like one DNA base switch for another.
Sure.
If this happens in a regular body cell, a somatic mutation, it might, down the line, lead to something like cancer in that person.
Okay.
But if it happens in sperm or egg cells, the germ cells, that's a genetic mutation. That could potentially be passed on to children.
And are some parts of the body more vulnerable than others? Definitely. The rule of thumb is the faster cells divide, the more sensitive they are. So things like, top of the list, the central nervous system, the blood-forming system, especially bone marrow and the gonads, the reproductive cells, also the lining of the gastrointestinal tract. Things with slower cell turnover, like muscle or mature bone, are less sensitive. That makes sense. Growth and rapid replacement mean more chances for damage during division.
What about actual dose levels? The source gives some thresholds for immediate effects.
Yeah, for acute short-term damage from a single whole body dose, the first clinically observable effects, like measurable changes in your blood count, start around 250 millisieverts, 250 millisieverts.
Okay, that's the start of noticeable harm. What about lethal doses?
The dose that would likely kill about 50% of people exposed without medical treatment, the LD50, is estimated around 4,000 millisieverts.
4,000 and a dose of 7,000 millisV or more delivered quickly is generally considered unsurvivable even with treatment. Those are stark numbers.
Yeah.
Okay, so we've covered the physics, the units, the biological damage. Now, the really practical question. Where do we actually get our dose from in everyday life? Let's start inside us. Are we naturally radioactive? We are. That's Standard Man. He contains naturally occurring radioactive isotopes. The total activity inside him is around 9,000 becquerels.
9,000 decays every second naturally inside us. From what? Mostly two things. Potassium-40, that accounts for about 4,500 BQ, and carbon-14, about 3,800 BQ. Potassium and carbon, essential elements.
Exactly. And it's not spread evenly. Potassium-40, for example, concentrates in muscle.
Okay, so there's a significant internal dose just from being alive. How does that compare to external sources when you add everything up for an average person?
Well, looking at average figures like those for Germany used in the source, the total average effective dose per person per year is about 2.4 millisievert to 2.4 millisv.
Okay, 2.4 millisieverts total. How much is internal versus external?
The internal part, from the stuff inside us plus what we inhale or ingest, is roughly 1.6 millisv per year. The external part, from cosmic rays and radiation from the ground, is about 0.8 millisv per year.
So the internal dose is actually twice the external dose on average.
Yeah, the natural background radiation we carry within us or breathe in is the bigger chunk.
And drilling down into that internal dose, thinking about that quality factor of 20 for alpha,
Yeah.
what's the single biggest contributor?
This is probably the most surprising takeaway for many people. It's radon.
Radon gas.
Yes. Specifically, inhaling radon gas and its radioactive decay products, which happens mostly indoors in our homes and buildings. That alone accounts for about 1.3 millisv per year on average.
1.3 millisv. That's more than half the entire average background dose.
It is, over 50%. And because radon's decay products are alpha emitters, Q20, they deposit a lot of damaging energy very locally when inhaled.
So which organ gets hit hardest by this indoor radon?
The lungs, definitely. The decay products, which are tiny radioactive particles, get trapped in the lung lining. The source estimates the lung tissue itself gets an equivalent dose of around 12 millisv per year, much higher than the whole body average, specifically because of radon.
Wow. So the biggest natural radiation risk for most people comes from the air inside their own house.
Largely, yes. It seeps in from the ground, gets trapped.
Okay, shifting gears to artificial man-made sources. What's the largest contributor there on average?
Medical procedures, by far. Specifically diagnostic X-rays.
Really? More than nuclear power or fallout?
Way more on an average population basis. The average dose from X-ray diagnostics is estimated at around 1.5 millisv per year.
1.5 millisv, that's almost as much as the entire natural internal dose and significantly more than the external natural dose.
Exactly. It's approaching 2/3 of the total natural background dose. It really dwarfs the average contribution from nuclear facilities or the lingering fallout from old weapons tests or accidents like Chernobyl when averaged over the whole population.
That absolutely reframes where the significant exposures are for most people. Less about external threats, more about natural internal sources like radon and the medical procedures we undergo.
It does. Understanding the units, especially the Sievert and that Q factor for alpha, really points you toward radon. And understanding the averages highlights the impact of medical X-rays. Okay, so wrapping this up, the key things to remember seem to be the Sievert matters because different radiation types do different amounts of damage for the same energy that Q factor, especially alpha's Q20.
Right.
And biologically rapidly dividing cells are most sensitive. And maybe the biggest surprise, our largest single source of natural radiation exposure isn't cosmic rays or food, it's radon gas accumulating in our homes, hitting our lungs with alpha particles. Which leads to a really practical final thought, doesn't it?
Yeah.
If that huge chunk of our dose, 1.3 millisv per year, comes from radon, indoors radon originating from the ground and building materials, what steps could you actually take? Simple things, maybe. Improving ventilation in basements, being mindful of building materials. Granite, for instance, has higher natural uranium-radium content. Could these significantly lower your personal annual dose?
That's a powerful takeaway. Knowing the source gives you potential control, something for all of us to think about.